pleasure for me to give my second talk here. And actually, this will be a sequel of the first talk, Virtual Knot Theory Methods in Classical Topology. I will try to make this talk self-contained, and this will be devoted to knots in the full torus. This is a joint work with my very good collaborators. They are both here. Kim Sarah, and really she is a heroic person because in Korea it's late night today. It's late night now, and I'm really happy that she's here. And also Kim Sung-John. Well, now Kim Sung-John can be thought of as a Muscovite, so he works in Moscow for some time. Well, actually, the talk is entitled Virtual Knot Theory Methods. And you can ask why, well, what about virtual knot theory? Why virtual knot theory? Actually, because virtual knots are the source of parity. In fact, for virtual knots, we have a way of distinguishing between even crossings and odd crossings. And actually, for virtual knots in many respects behave like links, and we can get many invariants which have never been seen before for classical knot theory, like picture valued invariants, invariants valued in some groups which actually have nothing to do with the fundamental group, and so on. So, for the first time, when I gave my first talk, I actually concentrated on free knots and free links. I just mentioned my further directions. And actually, I constructed an invariant of free knots and free links and valued in free groups or products of free groups somewhere. Well, and now actually I'm going to speak about more classical objects. Actually, the objects I'm going to touch today will be just knots in the full torus. Well, you can ask me maybe why in the full torus. The answer is very, very easy, because if we have just a full torus, this is the simplest thing, simplest three-dimensional thing when we can imagine some Z2 homology. Actually, you can argue whether it can be RP3. Actually, one student of mine is now working in RP3, and actually, if we have some parity, we can look at odd crossings, something called odd. And actually, we may try to look at why do we have, say, linking number for linking coefficients for links and don't have it for knots. Well, because if we try to count something for knots, in the classical case, crossing can just disappear after the first Reidemeister moves. And odd things are somehow stable. And possibly you can consider this talk as a beginning of a series of talks, I hope, at different seminars, not only here, I think, about how to make invariants non-commutative. Well, actually, in topology, not necessarily in knot theory, we are trying to count something. For example, we can count crossings between two link components. It may be the simplest thing with pluses and minuses, and we get a linking number. And now I want to have everything commutative. Well, here I'm mentioning the parity bracket, and actually the parity bracket is something valued in, I would say, knot diagrams or linear combinations of knot diagrams. But in fact, knot diagrams are quite similar to free groups. Actually, for free groups, or maybe not exactly free groups, but also free products of some groups. We have the following phenomena, which makes knots very similar to groups. Actually, if a diagram is complicated enough, then it reproduces itself. So this is the formula I like most. The bracket of K equals K. So what does it mean? It means that we want to introduce a certain way of constructing a knot invariant out of a knot diagram. Well, an invariant will be a certain state sum. However, we don't want to evaluate it completely to get numbers. I'm very happy of not getting numbers. I'm very happy of getting diagrams with linear coefficients. And under some circumstances, the bracket of k equals k itself. And this means actually that whatever diagram of not equivalent to k we take, well, its bracket will be k again. And why is it similar to groups? Well, because if we look at free groups, we can have a unique minimal representative, meaning we have a reduced word. Having a reduced word, we can say, okay, this reduced word appears in any word equivalent to that. Actually, we can cancel something like a and a to the minus 1 and get to the unique representative. This is something like diamond lemma. And here is the formal definition of the bracket. We will not need it for today's invariant. Today's invariant will be valued almost in a free group, but this is just for the sake of similarity. Actually, what I do here is I take a diagram. Well, actually, here I will need a diagram to be a graph with opposite crossing structure. And I want to take crossings which can be even or odd. Well, what are even crossings I can tell in a moment. But you can imagine that this is something like pure crossings for links and mixed crossings for different link components. So pure are even and mixed are odd. And now I want to take the bracket to be the sum of all smoothings of even crossings, so I don't touch odd crossings, and only those smoothing which give me a one component thing. And I'm lazy, so I don't want to deal with integral coefficients. I want to deal with Z2. And I want to consider that modular Reidemeister 2 equivalence, which actually means that Reidemeister 2 is similar to something like cancellation in a free group. So we can just cancel two adjacent crossings which are similar. Okay, and in a proper sense, you can ask, why not classical links? Because for classical links, we don't have an evident parity. Well, you can ask, we don't have an evident parity for classical knots, but we do have for links. Right, but if you try to do such graphs for diagrams on the plane, then somehow diagrams on the plane, when we forget over-under informations, well, we will have bygones or something. Well, and actually, the most interesting and the most striking example is the example we are going to discuss today. Well, this will be the full torus. Actually, this the thickened cylinder, we can say, okay. And the parity bracket, well, it doesn't work immediately for the circle times, well, for the cylinder. There are some reasons for that. I'm not going to dwell into that. But what I'm going to say today is that we are going to get a map from free knots to free groups. And actually, this was done last time. And today I will be talking not about free groups, but not about free knots, but about knots in the full torus. And when we construct a map from free knots to free groups, we get many things for free. How can you imagine that? Well, actually, if we consider say a free group, okay, then we can ask, what about the invertibility problem? Well, if you teach a child to some elements of knot theory, you can say, okay, so these knots are not invertible, and you can say, okay, if I want to construct an invariant and I want to say that it's hard enough, that it's harder than the Alexander polynomial, or it's harder than the Jones polynomial, I can say, okay, I can detect, for example, the knot invertibility. And what's the easiest way of detecting knot invertibility? well, it's not that easy to teach school children to that, right? Unlike, for example, even Kaufman bracket, we can do something with that. It's completely combinatorial. But if we deal with free groups and the children we are dealing with are, well, no free groups, then we can say, okay, well, for free groups, we can invert a word. Maybe invert word, maybe invert some letters, but we can have something like automorphism or anti-automorphism, and we can easily imagine that something is not invertible if it's not palindromic in some sense. So, well, and you see, now I'm going to argue that any Z2 yields free groups. And this is actually very ambitious because here we have a very large project of finding free group structures as invariants of everything. Well, next steps will be classical knots without any cylinder, maybe three manifolds and other things. So actually, if we have some Z2 homology, which is not that difficult to create, say, if we have Z homology, then I argue that we will get something like free group. And actually, this will not be exactly a free group. This will be a free product of Z2s or something like that. And actually, what I need from that group is that the group will have an exponential growth, excuse me for the typo, and this is very easy to work with. You will see a Cayley graph, and this will be a funny picture. And well, if we have some Z2 homology, we can do many things. Okay. Well, and now I'm going to consider long knots in the cylinder. Well, okay, of course, knotoid people can easily recognize knotoids. And if you're doing knotoids, you can just take a map from knotoids to long knots in the cylinder, so you can get all invariants back. Also, you can imagine that you are doing links where one component is known to be trivial. Then again, you have this picture. Or you can imagine that you have Brownian links or many other things. And actually, I want to advertise two things. So first of all, we have our research group, I would say, and we're going to meet on Saturday with my colleagues from Moscow and Korea and maybe China, and we will meet on Sunday with Lou. Actually, and the other thing I want to realize just now is, well, I'm very happy to see a recent brilliant paper by Lisa Piccirillo and Ciprian Manolescu about their attempts to create knots, to create some four manifolds with some specific structures. Well, actually, well, of course, we can get three manifolds out of knots. And actually, we can also get four manifolds. And people, well, I apologize because I'm just maybe a beginner in three manifolds, and there are four manifolds, and there are very respected people knowing much more than I do than in four manifolds. But anyway, I would say that, of course, knots in the cylinder are very respected objects because we can do lots of surgeries. We can do lots of manifolds with one torus component. So we will concentrate on such long knots in the cylinder or something like thickened torus. So we will do that. And we will consider such diagrams. And you see, if we have such diagrams, we can construct the Gauss diagram. We construct the Gauss diagram on the line because this diagram is long. We have a long knot. We have a beginning and we have an end. And actually here on the picture, you see that some chords are even and some chords are odd. Actually, the even ones are red and the odd ones are black. And actually, the fact that there are some red chords and black chords is due to the fact that we have some non-trivial homology. In fact, if we want to consider a Gauss diagram of a classical knot, you can see that each of that chord is even in the sense that it intersects evenly many chords. Or maybe if you don't like the word intersect, for graphs where really edges do not intersect unless they share a vertex, you can say they are linked, or you can say their endpoints alternate or somehow, you see here we have black chords which are odd and red chords which are even. And actually, maybe one of the first knot theorists was Carl Friedrich Gauss, and actually he mentioned he proved a beautiful theorem that if we consider a Gauss diagram of a classical knot, then all chords have to be even. Even he made a mistake by thinking that this condition should be not only necessary but sufficient. So actually, and when great people make mistakes, usually it leads to something. Actually, not all even diagrams are planar, to the best of my knowledge, the planarity for just Gauss codes of curves was first, the planarity criterion was first found by Max Dehn more than 100 years ago, but still more than 100 years after Gauss. And actually, since Dehn, maybe all the 20th century, we had a history of new and yet more proofs and yet more criteria of planarity. This is something like quadratic reciprocity law, when we have lots of new proofs for 2 centuries. Well, and here we see that we have red and black crossings, and we can define them with respect to the role how many chords are linked with the given chord. However, we can take another rule which is similar to that and which fits nicely to our axioms. And this other rule is as follows. We can look at the homotopy class of our crossing. So if we have a crossing, then we can split our diagram into 2 halves. And actually, each of those halves has its homology class as a curve on a cylinder, say. Of course, we can close it up. And actually, we have even not only one parity, but maybe 2 parities. One of them turns out to be trivial, but again, this is a sort of parity. And the more homology you have, the more parities you have. And when we introduce our invariants, we will distinguish between 2 letters, or maybe 3 letters, or maybe something like not so many letters. And you see, if you have a huge amount of homology, then you can upgrade our invariants as much as, very much. But here you see what I'm really interested in is that the group is of exponential growth, and it's very easy to work with. So for me, for example, Z2 star Z2 star Z2 is good enough. And if we take just Z2 star Z2, this is something like infinite dihedral group. Well, not exactly, but similar. And from Gromov's point of view, if we look from far away, it's just the Z. So, if we look just as Z star Z, this is not so good. But Z star Z star Z, it's already, a group which contains any free groups inside. So I just suggest to have called these groups free by abusing notation a little bit. Okay, actually the group will appear in a moment. And here is the rule for writing a word. Actually, we consider oriented long knot diagram on the cylinder, and we traverse that knot. And I want to emphasize that there will be even chords and odd chords. Even chords are somehow some chords which can disappear, and I will call them A, and A will be a reflection, so A squared equals 1 always. And all other chords will be called C or B or C prime or B prime. I do not pretend this group to be the most perfect you can imagine. It will be easy to get some upgrades. And actually, we distinguish between types of chords depending on how many even or odd chords it intersects. Well, it can intersect evenly many even chords, evenly many odd chords. And also, well, if we write down a word, well, its endpoints can be in odd position or in an even position. Actually, if a chord is odd, then it intersects oddly chords chords, and this means that both positions have the same parity. For example, if I take a chord which connects point number 3 to point number 5, then it is linked with only one chord which connects something to point number 4. So and the 3 and 5 are congruent modulo 2. And so we make a distinction between odd position and even position. So this is a very easy rule. And actually, we will construct a group which maybe has something to do with some fundamental group, but it's not obvious. So for example, for virtual knots, we have various ways of upgrading the fundamental group by adding relations of virtual crossings or adding new things at classical crossings. But this thing, well, they have something to do with topology. And here it's completely combinatorial thing. And actually, it's combinatorial and it's easy to work with. Because if we deal with the fundamental group, then we associate a whole group to a knot. Well, and we get some group, and we know that it's, abelianization is Z or, of course, okay, Z. And, we can, of course, say that we have a longitude, but it's not very easy to work with. Of course, the word problem is solvable, but still it's not very easy. And now I want to coin a certain group fixed once forever, and I want all my invariants to be valued in this concrete group. And actually, we will see that this, if we change, for example, a crossing, if we switch a crossing in a certain knot, then the fundamental group changes not very nicely. For example, the 3 coloring or other Fox colorings are not very good with respect to the crossing change. And what happens in my group? Well, we just replace one letter with another one or something like that. And here are the letters for endpoints. Here is my vocabulary. So A will be even, and B is something, all other things are odd, and odd crossing in even position. And also I want to make a distinction between over crossings and under crossings. Actually, when we deal with the second Reidemeister mode, then of course 2 consequent over crossings can cancel out. And so this means that we make a distinction between over crossings and under crossings. Important remark, we have to make this distinction because otherwise the invariant would be something like an invariant of a curve up to homotopy, a curve on a solid torus. Well, and that's not interesting. Well, curves in the solid torus, I think we know the homotopy. the first homotopy group of the solid torus. And so if we make some distinction between over and under thing, that will be much more fun. So here is the vocabulary how to use A, B, and C. Now I want to upgrade my notation a bit later. I want to make a distinction between first type and second type. And here is an example. Here is an example of a knot in the full torus. Actually, I'd better say that this is a knot in a thickened cylinder. And so I start from the top to the bottom, and I go this way, and I get the following word. So you see here we have 3 even chords, and we have 2 odd chords. Here, by even, I mean not the type of the chord. So is it, not, well, I'm not meaning that this chord is even, but I'm rather meaning the position. So 1 is odd, 2 is even, and so on. So why have I drawn this link? Well, because just we can straighten one component and pull its end to the infinity, and we get the black component to be here on the thickened torus. So here is the word we get. Actually, many A's can get canceled, and actually here we can do quite a bit, because C prime and B prime cannot be easily canceled, and possibly you can figure out what the relations would be. And actually, the relations for Reidemeister 2 are more or less already here, because A squared will be equal to 1, and B and B to the minus 1 will cancel to each other. The same for C and C to the minus 1. But for Reidemeister 3, we will need some relations. These relations are not a commutativity relation, but as we will see further, this group will be almost free. Well, in fact, we can make much more distinction between chords. For example, here we have not just, here we have not just Z2 homology, but we have a homology over Z. And this means that we can get not only a chord parity, but also a chord index. But if we have a chord index, wow, we will get infinitely many generators indexed by integers. Well, I don't want to have so many generators, but of course this will make theory more fun. But for my purposes, this is enough. So here is our main hero. Well, maybe first main hero, G2 primes. Well, the notation comes from some historical remarks, because maybe last time I was talking about the group G1, G prime. And actually, I just remind that in the last talk, I was talking about 3 knots, and I considered some groups, some invariants in 3 steps. So 1 step was just a bare count. I was counting odd crossings. I was counting odd crossings with a certain way of assigning signs to those odd crossings, so I could get an integer number. And actually, this integer number turned out to be something like cobordism invariance for 3 knots. And actually, we can get cobordism invariance. But I invented that invariant for 3 knots, which was an integer number, in an attempt of getting an invariant valued in a certain group. But that group turned out to be Z star Z, almost Z. Oh, excuse me, Z2 time, Z2 star Z2. And Z2 star Z2 is a group of just linear growth, and it's not very interesting. But then I saw that we can upgrade something by adding more signs or more over under structure or something like that, and get such groups. So here is a G2 primes. That's welcome. And actually having not in the long, having a knot in the full torus, we can write down such a word as said above. and we get something here. And of course, our theorem will be that this is this will be an invariant under Reidemeister moves. Well, and actually, for the not drawn before, we get this, and of course, you can start asking many questions and getting immediate answers. For example, what about the not invertibility? Well, something like palindromic things. So invert something, maybe something will change. Well, I mean, maybe we can rename some letters. You can ask, what about mutations? Well, again, we cut something and paste something, but we can handle what happens. Of course, crossing changes also. And even for cobordism, we can do quite a bit. And well, maybe not everything is written here. I will give some references at the end of the talk. But you see, such groups which are similar to free groups are very easy to handle. Actually, we can rewrite this group with so many generators by rewriting primes as something without primes, so we can get this group, and then we will see that this is almost a free group. Actually, this is the Kelly graph. So you see we have a blue part and we have a green part, and you see A is something like a switch between the green part and the blue part. And here on the top and on the bottom, we have two free groups. Actually, the blue arrows are B's and the black arrows are C's. And of course, if you look at that, you will see all the relations which appeared before. Okay, and it's easy to see that this is just a group here. Okay, and now, of course, the theorem is that this is an invariant. And this comes from the Bear count. This comes from some straightforward check. Maybe the only thing I should comment on is the third Reidemeister move. And you see, for the third Reidemeister move, we have to mention that either it happens for all three even chords, and then we have actually nothing to do because AA equals AA, and actually it equals 1. And also, we have some relations when we have three chords, one even and two odd ones. And this means that we have one A and something, and this something switch somehow. And for example, we can have relations like C prime equals AC to the minus 1A. And this is some conjugation by A. And those relations are actually those which correspond to three positions for Reidemeister, for the Reidemeister 3. Actually, and here is more or less the proof. And now I want to give some examples. And after that, I will start talking about further applications and actually further dreams. And maybe concerning examples, I can ask Sanjon and Sarah to say some words, because my co-authors were spending quite a lot of time calculating everything very quietly. And here I suggest Sanjon maybe to comment on the slides concerning the examples. Okay, and actually some further group will emerge here, some further group when we do some upgrade for letters. So Sanjon, please start. Okay, commenting on the other group.
Excuse me, I cannot understand you. You mean?
Well, I mean, it would be better for you to tell more about other groups when we have signs and other things. I mean, those slides when we have G3 prime and G bar and other things. So so you were doing that more carefully, and you can show the examples. And after your part, I will return and talk about some further problems. Here are the slides. You can share your screen if you wish. So here,
Friend, please begin. We are not planning about that, so I.
okay. Well, if so, I can just mention here that we can take into account something more, just a small bit of information. So actually, Gauss diagrams and chord diagrams have many bits of information. For example, the arrow direction, or also the right number, or also where that goes from the left to the right, or something like that. So here we can take the sign, and just I want to make some distinction between two A's. So I want to get rid of the relation a squared equals 1, so I can do this, and so then I have a chord D, and I want to have this sign, which is the right number, and then I can get this, and then I can get B prime. Well, and actually this is a bit boring, but anyway, we will have just a similar thing, but instead of A squared equals 1, we'll have the commutativity relation, like just a to the minus 1 equals 1, or maybe a equals AA. So nothing similar, but the group will be richer, and actually yet another. So we have this and we have that. So actually here are all those species of groups, and all those species of mappings. So if we had, say, phi double prime, so this was a mapping to the group G double prime, and we can have phi bar of phi twiddle. So here is our main example we had in the bird. Not quite, I think. This is another example. This is another example corresponding to a knot on the full torus. Or knot in the thickened cylinder. So here we write down two knots, K2 and K1. Here are examples. K2 prime maybe and K1 prime. So we have here, and these are long knot diagrams from figure 3. So we have such words like this. And actually, of course, if we have something like free groups, we can easily count the word length. And actually, and the minimal representative in the free group comes just from a reduced word, right? So, for example, if we look at those words which correspond to these two paths, we will have something like that. We go C, B to the minus 1, B to the minus 1, C. So this means that we have 4 crossings, at least 4, at least 2 crossings, at least 4 endpoints. So two chords will give rise to 4 passing through crossings. And here is another word. So we have B to the minus 1, which means that we go along the blue chord in the opposite direction and something like that. So here C's become small. But of course, walks in this easy graphs are very easy to distinguish between. And of course, we know how the work changes if we do something like crossing change. So we can do quite a lot of things here. And actually here, if I look at this group called G twiddle, so we have such relations, and actually our element will always get to the following subgroup, and actually this subgroup is nothing but Z star Z. You can see it from this picture of the Kelly graph. So you see here we have A, and A switches between the red part and the blue part, and if we take the red part only, then it will be just the free group in 2 generators. And of course, if we have a certain word, then it will have evenly many A's, which means that we will just stay in the red part. So this means that we will get an invariant value here. And actually, this is a very simple thing, but what we need our group to have an exponential growth. On the other hand, we need this group to be easy to manage. So this is almost free group. Okay, and here we can, I can give you an example of what to do with invertibility of long knots on the cylinder. Well, if we have a word, we can write down the word in the opposite direction, like here. And you see, if we have something like this, then the word in the opposite direction will be read just in the opposite direction. So of course, these words are not the same. So we get, so for free groups, we get non-invertibility for free. You can ask me, well, we know the non-invertibility of the hop link, for example, if we change just one component. So if we have a positive hop link, then we invert one component and we get the negative hop link, and we know from school that one of them has linking number +1 and the other one has linking number -1. But well, this is something which deals with changing one component. But on the cylinder, you see, we can change the orientation of the other component. And actually, in one situation, actually the invariant is not sensitive to the orientation change for one component. But we can make it sensitive. It's not hard. So we can do many things, and we get invertibility for free. So here is the formal corollary, here is the formal thing. Well, actually, I want to spend maybe almost half of my talk for further directions and for some problems. So here is the non-invertibility of the knot shown in figure 5. So here is the figure 5. And of course, we have some non-invertibility. And here I would like to make a warning about classical knots. Well, in fact, our goal, of course, and this by some technical reasons, maybe the next talk will be classical one-component knots, though I'm very happy with links already. For knots, you can imagine the following. Well, virtual long knots do not commute. Actually, they almost never commute, as proved first by myself and then by Micah Chrisman. But classical knots always commute. So and now we want to write down a word in some generators, and you see, if we have a free group, then nothing commutes. Well, unless we have just different exponents of the same word. Well, and this means actually that if we try to make words out of classical knots, then we should not expect to have a homomorphism. So this means that the way of getting product will be more complicated. So, for example, we can try to get some homology around the classical knot, but this way of constructing homology of things and even things will depend on some factors in the factorization. So, for example, we shouldn't expect that something for K1, K2 will be exactly K1, K2. But for something on the torus, we have this non-commutativity phenomena still, and actually we can easily see whether some chords can be canceled. And actually, in order to see this more complicated group, for the group without, for the simple group, excuse me, word simple, for the word simple, for the easy group. We had just this, and for a more complicated group, we have we can easily judge whether we can cancel some B's. And for example, we can never cancel two B's if there is exactly one A between them. And actually, if we have evenly many A's and C's between them, then they can be canceled. So actually, this is something very close to the to groups called G and K. And actually, for groups G and K, where I have lots of topological invariants valued in, we had something like indices, and we could extract many invariants valued in free groups because there are many maps from G and Ks onto free groups. But actually, G and K methods are not very friendly to knot closures. So actually, for G and K methods, we needed something like braids and strands of braids, but actually, they didn't behave nicely when we were when we had something like maxima and minima. So, but here everything is okay, and everything is okay with Reidemeister 1 move. If we look at this word, we can actually see that nothing cancels. Nothing cancels here because, for example, if we want to see whether this B and this B can be canceled, excuse me, just a moment. There are oddly many. Excuse me, no. B cannot be cancelled with B. B can be cancelled only with B to the -1. But if we look at B and B to the -1 here, we will see just one C here. So actually, this means that this word is minimal. This word is minimal in the sense that we cannot get smaller number of crossings. And you see, when we get something like polynomial invariance or even knot homology, we can judge about the knot. We can say, okay, here we have the span of the Kaufman bracket to be equal to something, and this means that the number of crossing is at least something, but we cannot see the trefoil inside the knot. We cannot see figure 8 inside the knot. But words in the free group are just talking by themselves. So if we have a word, this means that whenever we take something like, if we have an equivalent knot, then it will have an equivalent word, and it will have some this as a subgroup, well, as a subword in the word. So this means that we can draw something like cats, as I did last time. Well, we can draw cats, and if maybe I can find a picture of a cat somewhere else, because I still have quite a lot of time for today. So actually, cats are very good for Reidemeister moves, because if a diagram is complicated enough, then it realizes itself. So we see it at the level of free groups, and we can see it. We can see it at the level of Reidemeister moves. So just a moment. I will show a cat. I think this was my first talk, maybe in March, I think. So I am sharing my screen. So this should be virtual knot methods in classical topology number 1, I think. Yeah, this one. Okay, and actually here are the cats. So you see here is the picture how cats correspond to free groups. So we are taking a knot diagram like this. This cannot be decreased in one step. And so if we can not decrease, then we can possibly increase. We do that. And we can see the initial knot diagram by just smoothing some crossings. And actually, this is the essence of the bracket. We take a certain state sum for the diagram, but in this state sum, we don't evaluate everything to numbers. We evaluate it to diagrams. And you see, we can see this picture with all its geometric features inside any diagram like this. Of course, this is not the case for classical knots because of, say, the culprit knot. But this may be the case, at least for the unknot, in the situation, for example, for grid diagrams. So this suggests that we have to look for further, for other ways, not only Reidemeister ways of diagrams of classical knots. And well, at least for knots on the cylinder, we have these things. Maybe not in the form of cats, which could be more pleasant, but in the form of words like this. So if we have a word, then we have its reduced form when nothing can be cancelled, say in the free group. And if we take a word which is equal in the group, we can cancel out whatever possible, and we will get to this minimal representative. So, here are the slides of my first talk, and here we had some examples of, say, chord diagrams which have this property bracket of k equals k, or maybe bracket of d equals d, meaning that this diagram will always appear in any knot equivalent to that. And actually, there are many other features, for example, for cobordism. So we have a sort of Fox conjecture saying that if something is sliced, then it's easily sliced. Easily means that with us, it's sliced without triple points and cusps. I'm not going to decipher the meaning of cobordism because this is not a talk about cobordism. Maybe some talk number 3 or 4 will be about cobordisms. But just a moment. Well, I'm returning to my initial slides of today's talk, and I think here they are. I think you can see the slides of today's talk, and actually here is the remark saying that if we invert the orientation of the cylinder core, then it changes nothing. Then it changes nothing in the diagram. So, and this changes nothing in the word. So, again, the summary. So we have a certain group which behaves in a way very similar to a free group. Actually, this has a free group as a subgroup of something like index 2. So it's a free group. And we write down a certain word just with respect to some easy rules like this. And so our long knot in the cylinder will get a map in this free group. So what's next? Well, if there are students here, I can say a couple of words how to, well, write a diploma or something like that. Well, just take not parities, but indices. If you have Z homology, then you can get indices which allow our variables to be indexed by integer numbers. So we will have a more fancy group. And for example, there are some nice non-trivial relations. For example, if we have some chords which take part in the third Reidemeister move, then their indices have to sum up to 0. For example, 7 minus 3 minus 4. And of course, you can go much farther away in this direction and get much more complicated invariants, but I'm happy with what I have. Actually, one more thing is that we can find some hidden crossings. What do I mean by that? Well, if we are on the cylinder, you see, if we zoom into here, if we make some magnification, then we see something virtual. So we get this line and we get this. This is not counted as an intersection, but we can do the following. Well, what are just classical crossings if we are in the cylinder? We can take the core line of the cylinder and take a line passing through this core line. And for example, this crossing gives us two branches of the knot, which are on the same ray. But maybe we should not take rays, we can take lines. And we can take for crossing to be something which is some two branches which are on opposite ends, on opposite rays of some line. And well, having that, we will have many hidden crossings, and maybe in some sense, hidden can be thought of as odd ones, and not hidden will be even ones. So, but actually this is something like work in progress, and if there is a student, I will be happy to give something like that. But actually we can do further. We can look at crossings whose angular not crossings, but branches whose angular coordinate differs not by 2 pi and not by pi, but something like 2 pi over q. And maybe having 2 pi over q, this will mean that we will have many species of different crossings, and they will have, I don't know, parities, indices, or whatever else. Well, actually, when we calculate brackets and we want to say, okay, quantum TQFTs and say Witten, Reshetich, Turaev teach us that if we evaluate many things coming from physics, we should get something like numbers. Well, why can we get numbers? Well, occasionally, if we have something like Murakami, Otsuki, Yamada, or say Kuperberg spiders, then we can undo the spiders with respect to certain rules, and finally we will evaluate it to a number or maybe a polynomial. For me, a polynomial is just a collection of numbers. But if we take a certain picture of Kuperberg or Murakami, Otsuki, Yamada and draw it on the surface, we will see that the rules we actually have, skein relations, do not necessarily lead us to pictures which give exact evaluations in numbers or polynomials. We can get pictures, and actually we are happy with that pictures, because these pictures can tell us much more about the diagram than just a number or a polynomial. This was a work which was initiated by myself, and there are some things where we had invariants valued in pictures in my works with Lou, for example, Kuperberg. But you see, there are many other brackets, and actually when I was talking about this main formula I love the most, the main formula, which is the bracket of k equals k, and I said, well, the parity bracket is, well, in some cases this doesn't work very well. For example, if we have all odd crossings, then the parity bracket of k equals k itself here. Why? Well, because we have nothing to switch. Nothing to smooth. So all crossings are odd. This means that we have nothing to smooth, and the bracket of k equals k itself. But assume we have all crossings which are even. Then it will be something boring. It will evaluate to some number, or even in this case, this bracket is not good for all even things. But there are many other brackets. For example, Cooper-Berg brackets, well, maybe up to some small lie, they behave the same way. I mean, bracket of k is in some sense very similar to k itself. And this means that if we look at such brackets, we will see quite a lot of information about any knot diagrams. And you will see that these things are very similar to free groups. And actually, this works already on the cylinder. So these are many projects, and any student can take it and get more invariants. And now I want to say more about further steps and work in progress just now. Actually, of course, you can ask, what about classical knots and classical lengths? Well, the problem is that where to take such an obvious parity. I mean, so for actually for Reidemeister knot theory, we have something to project to. For example, if we are in R3, then we can project to R2. But if we are in the full torus, we can project to the cylinder. But if we are in free space, there is no such obvious projection which would give us some parity. And actually, we have to create this projection. And now we're trying to choose among various nice ways to project. Actually, we can create a cylinder. We can go along the knot and create some cylinder by going around. Or other way, we can get a map from knots to two knots. Something is written about that in our book, Invariants and Pictures. If we don't have an unlinked component, we can take some Seifert surface and try to do something around this Seifert surface. This was partially done in my work with Micah Crisp. So we can do something for classical knots and classical links, but technically it will take some more time and maybe some more talks. Now, what about three manifold invariants? Well, okay, I can just sketch some very initial ideas about three manifold invariants, but for me it would be better to deal not just with three manifolds, but I would say with something having virtual things inside, or maybe virtual free manifolds. Well, I want to have some source of Z2 things, and actually, you see. In my picture, I got a map, something like if we have a knot, and if we have something like a source of Z2 homology, like the full torus, then we get a map from this with this knot to the free group. Well, not exactly free, but something like that. So we get a word, say, P of K, somewhere here. But now you see, what do usually people aim at if they want to do Kirby calculus? Well, the main thing to overcome the Kirby calculus is, of course, the second Kirby move. And the first simple idea which comes to my mind is that, well, if we have something like this, then this knot gives us a generator alpha, and this knot gives us the generator beta, and we get this group maybe like this, and we can take the relations alpha and beta, and maybe this will be the same as the group with the relations alpha beta and beta. Okay, and so this makes our hopes much more manageable than just some things like John Swenson idempotent. Of course, there is a whole great theory of John Swenson idempotent due to Luke Hoffman and Heather Dye, but this is too much complicated, I think. And well, if we have knots in the thickness cylinder, we can try to do John Swenson idempotent, but this is not a very much manageable if we do with classical links, because actually we have to splice, we have to put something like idempotence into classical links. Okay, I'm going to conclude, and actually these things seem to be much more manageable. So I'm now mentioning work in progress. So Cobordis work well already. We have just to write a paper. Brunian braids have components, so have trivial components, so we get something on the cylinder. And now a famous joke due to Lou that categorification is something when we get cats. So this means that we can get linear spaces instead of coefficients, but rather let's take free groups or node diagrams instead of coefficients. And free groups have much more to do with categories than just. Now I want to finish with something from Lou's talk. If we take some tensor rules for a number of colorings of a graph, then these tensor rules can give us to a positive integer number, or maybe they can give us a negative integer number, and we can say, okay, some crossings have some colorings or some tensors should be counted as something negative, but possibly we have cat colorings, and cat is something instead of a number. So the main goal is to make cats whenever we see numbers. So this means we want to have cats or free groups instead of characteristic classes, instead of intersections in homology, instead of everything. So of course, these steps are the next ones, actually here are their references. So these two references are just about my talks. Okay, so my time is up.
Well, okay, Vasily, thank you very much. We're a bit over time, so I don't think there will be time for questions now. But I'm sure Vasily would be more than happy to answer an email question. Is that true?
I'm absolutely happy, and we are going to have discussion. Well, actually, a sort of closed seminar on Saturday with our Moscow colleagues and Korean, Chinese colleagues, and on Sunday with Lou. So here, of course, we have lots of projects, and so very welcome to join us.
So
thank you very much, Vasily. Please remember to send us your slides.
Oh, yeah, sure. Yeah, sure. Son John will send all the slides, of course. Thank you very much.
Yeah, and perhaps I should thank all the Asian participants who have waited up to the early hours to join in.
Yeah, Son John is a Moscowite, but thanks, Sarah, thank you very much for joining us, and I'm very happy that AEG came to us, despite this very late time. Okay.
And just mention that next week we have Sergei Chmutov, who's going to talk on the groups,
Thomson
groups, and so that sounds very interesting. So, okay, so I'm going to stop now and wish everybody a happy evening.
Okay, thank you very much. Stay safe.
Thank you.
And enjoy mathematics. Thank you very much for coming.
Yeah. Bye now.
Bye.